I was sending things to my personal email so I could access it from everywhere.
Mm.
And it was saying, oh, you can't access your personal email, you need to verify it with your other.
If not, a private class. Oh, we don't have. Okay, okay.
I can give you a phone. This is just so the other contestants can watch.
No, that's okay.
So we put that on.
You explained everything.
I haven't explained this bit yet. So, right.
Yes.
Yes, I think
Your time is okay. Just tell me. Ja sam prepisala univerzitete, sigurno. Možemo još dodat master. Što? Da, master ne piše. Oni gore se već vidi. Gdje se gore vidi? A, ne vidi se gore. Ja sam master izgledala. Ja sam prepisala univerzitete. Ja ću samo u Zagrebu. Možemo još dodat master. Što? Da, master ne piše. Oni gore se već vidi. Gdje se gore vidi? A, ne vidi se gore. Ja sam master izgledala. Ja sam prepisala univerzitete. Ja ću samo u Zagrebu. Možemo još dodat master. Dobro. Skraćeno možda. Da, fakat master.
We okay to get the
Sad ću napisati još prije napisati.
we okay to get the
Sad ću napisati još prije napisati.
we okay to get the
Sad ću napisati još prije napisati.
we okay to get the
Sad ću napisati još prije napisati.
But he's on the table.
we okay to get the
Sad ću napisati još prije napisati.
But he's on the table.
we okay to get the
Sad ću napisati još prije napisati.
But he's on the table.
we okay to get the
Sad ću napisati još prije napisati.
But he's on the table.
we okay to get the
Sad ću napisati još prije napisati.
But he's on the table.
we okay to get the
Ne, nego gledam pitanje. Meni. Ko još? Đerđi, dobar dan. A gdje ste jučer?
Ovdje su predsjevarali.
A je, a cijeli dan? A u Čaku, da.
Nastavljak.
Padrov Đerđi. Kako je van nastavne? Puškari. Šta bi vi?
Ja sam bio i jučer. I sutra ću isto.
Dobro. Drago mi je, ja isto. Ok, pauze nek se tu pjava.
So just when it gets to the question and answer session, we need to talk into this because we were testing it yesterday. There's so we talk into this. The people presenting clearly, and then you will hear their response out of the speakers up here.
So I will take probably be the first one. So I come to each judge come here.
You can either come here or you can just take.
Okay, we don't. But we can pass. Okay. No, it is long enough. It is long enough. Okay. Okay. It may stand here. Okay.
See you fairly close up, and I'll put the camera up here as well so they can see.
Okay. Okay. Clear.
Ne treba
Ja imam u kompjuteru, nemam ne ja.
Nemam ja, kakve ime. Imate svi puno pitanja, ja ću
Ne treba pitati, to je čisto to li ja
Ovaj
sam pregledao.
četvrti Ahmedova. Koji? Četvrti i peti.
Koji bi se printao?
Ona se. Jani.
Budiš to je Jakub je moj, koji još je moj?
Jakub i ovaj prije njega Ahmed.
Ta dva su moja.
Ti nemate ništa.
A naši su sve da prvi, drugi.
Ne, ja sam, moj je prvi, vaš to jest moje prvi.
Dobro.
Možete vi koji hoćete pitati.
Good morning, everyone. My name
Njen
is
je drugi, moj je
Sarah.
treći.
Welcome to the second day of our 10th ASEC. We will start with master level student paper contest moderated by Mr. James Whitaker. Judges, please introduce yourselves.
Okay.
Do
you need this? No.
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 So is this okay? Okay, thank you very much. So just before we start, I just want to say thank you to everyone. This is my first time in Croatia and Zagreb. You have a very beautiful city. Thank you to Luca and all of the organizers at the University of Zagreb. It's been a really fantastic and insightful event so far. And you're about to see some of the leading papers across Europe. So I hope you have a wonderful day. Let's go to our first slide. So firstly, I just wanted to say a big thank you to Chevron. We have our global support from Chevron. They allow us to keep this program running. They allow us to have your student membership for free, and they're supporting a lot of other student initiatives around the world as well. So I want to say a big thank you to them as well. So for those in the audience, we really want to encourage you to participate in this program in the future. So just to do a quick overview of what the program entails, all of the speakers that you will see today, they have submitted abstracts and they have been reviewed, and then they have followed those up with full technical papers. So our judges today will be reviewing both the presentation and taking into consideration the work that was presented in their full technical papers as well. The presenters will have a maximum of 20 minutes to present their work, and then that will be followed by Q&A with our judges. No audience questions, unfortunately. And then we will move on to the next. So the winners from these, the Masters and the PhD competitions will be invited to our annual conference to present, to represent Europe in the international round of the competition. They will also be awarded $1,000, and hopefully we can help support them get to ATCE as well. Though the event will be hybrid so that we can keep as many people from around the world engaged in the program as possible. And all of our winners from today's session will also be invited to publish their work in One Petro. So that's a really great opportunity that's available to people as well. So I just want to talk a little bit more about the program because we really want to encourage more people. We know obviously we don't have an undergraduate division this year, but we really want to encourage more people. I was in a meeting last week and our SP president, Meg Mel, was talking very passionately about the student paper contest and wanting to see it continue. To the extent he actually brought his own technical paper that he presented as part of the student paper contest about 40 years ago. So he's really passionate about this, and we'd really like to encourage you to showcase your expertise going forward. So next up, we will now introduce our judges. So for the benefit of those people who are online, I will ask you to use the
Okay. My name is Nedeljka Gaurina Međimurec. I'm Professor Emerita, and I have been working at this faculty almost 43 years, teaching different subjects: drilling technology, drilling fluids, waste management in petroleum engineering, and so on. Thank you.
I wasn't sure if that was a train or feedback. Thank you.
Good morning, everybody. My name is Lidia Henčević. I'm, of course, petroleum engineer working at the Department of Petroleum Engineering as a full professor. And the scope of my research and interest is environmental protection and process control.
Good morning. My name is Sonja Koščak-Kolen. I'm a petroleum engineer as well. I work here at the Department of Petroleum Engineering. I'm assistant professor, and I my subjects are oil and gas production engineering, and I have specialized well testing and unconventional reservoirs.
Hello, everyone. As you can see, I came as a replacement for Professor Pašić, who is absent. And my field of interest in drilling engineering, offshore activities, well control, as well planning. And I have more than 40 years experience, field experience and educational experience. Thank you.
Fantastic. Thank you so much to our judges. As you can see, we have a rather unusual setup here to allow for everyone to present. We have a lot of people that we were hoping we were going to come today, but unfortunately, everyone knows how difficult it is to travel around. So these are our speakers today. We have one who will be in person, and we will be starting with our online versions, and they will be presented through a pre-recorded video followed by a live Q&A over Zoom. So we will get started with those. I will just see if Matt is with us. So on the screen, you'll be able to see the presentations. Okay, so Matt did message that he was running a bit late, but he's happy for his presentation to be shown, and he should be able to join us for the Q&A. So we will get started with our first of today's presentations from Matt Swaller, the Karlsruhe University of Technology in Germany, who will be presenting on the impact of brine salinity and ion type of the wettability of calcite in the presence of acid oil compounds. And one more note, I am not an engineer. These words are a mess to me. So my apologies for any mispronunciation along today.
Good morning. I'm very happy to present and discuss my results from the research I conducted during my master thesis. Because the wettability is such an important factor for secondary and tertiary recovery methods in oil reservoirs, I investigated the effect of brine salinity and ion type on the wettability of calcite in the presence of acid oil. Changing the wettability from oil wet to water wet increases the movable oil by reducing the residual oil, which results in higher reserves and a higher acid value. To investigate the shift from oil wet to water wet, I measured a range of contact angles at different systems of an oil drop on the rock surface using a high pressure drop analysis system and compared my results with the literature. The findings confirm the impact of the ion type as well as the overall ion concentration on the type and shift of wettability. Thereby, I could confirm that the ion type is of greater importance for the wettability of the rock than the overall ion concentration. I'd like to start with an overview of my work. Following, I will say a few words about the electric interactions happening between the rock surface and the fluids because it is the fundamental principle of wettability. After that, I will discuss my measurements in more detail, starting with the preparation of the experiment and the experimental setup. Next, I will discuss the results of the measurements. At the end, I will give a summary, share learnings, and will give recommendations for future experiments of this kind to investigate in more depth and with a wider range. In my experiments, I studied the wettability of a calcite sample with more than 40 different brine, oil, and rock treatment combinations. The impact on the wettability was examined by measuring the contact angle of the oil on the rock surface in the presence of different ions to see for which ion the contact angle changes from less than 90 degrees and water wet to more than 90 degrees and oil wet. The results show that divalent ions have a greater impact on the wettability than monovalent ions. Further, the literature reports increasing water wetness with higher ion concentrations, which could indeed be confirmed. Very interesting was that the contact angle measured during the experiments behaved partly opposite of expected, which could indicate either a conditioning effect affecting the results or that the calcite is not generally positively charged as many papers assume. As wettability is a result of surface tension, let's first have a look at the electric interactions. Wettability is a reflection of the relationship between the rock mineralogy and the fluids in the system. As carbonates have a more complex mineralogy and tend to be neutral or oil wet, the wettability of these rocks and its alteration is of importance for enhanced recovery methods. So to understand the effects determining the wettability, focus was given to the electric interactions taking place at the mineral oil, mineral brine, and brine oil interfaces. These interactions cause attractive or repulsive forces, which are essential for the strength and the size of the electric double layer that is located between the rock and the fluid surfaces and determines the wettability. This electric double layer is dependent on the electric charged ends in the fluid and at the rock surface. Carbonates primarily consist of calcium carbonate and dolomite, making the surface charge generally positive, contrary to sandstones, which often have a negative rock surface. The carbonate surface charge is determined by the amount of the positive calcium compared to the amount of the negative carbonate. For the brine charge, the concentration and the specific ion type are of importance. Cations like sodium, magnesium, or calcium are positively charged and tend to absorb on negative charged surfaces, while anions like sulfate are negatively charged, tending to absorb on positive surfaces. Ions can thereby also have different charged concentrations. Divalent ions have 2 charges, while monovalent ions have only 1 charge. The charge of crude oils is dependent on their composition. They often contain polar compounds, which can cause a more positive or negative charge. However, crude oils with a higher number of acid compounds are more common, especially if the crudes get heavier, because heavy crudes often contain more sulfur compounds, and these oils then tend to wet carbonates. For the experiments, model oils were used. I prepared the base solution out of C16, C20 and C24. For model oil 0, no acids were added to the base solution. For model oil 1, I added 1 weight percent pentanoic acid, and for model oil 5, I added 5 weight percent pentanoic acid. The brines tested in the experiment consisted of 4 different ions: sodium as a monovalent ion, calcium and magnesium as divalent cations, and sulfate as a divalent anion. Each ion was thereby blended at 3 and 10% ion concentration. And to create a base case, I also tested distilled water. The ions and the oils were then tested at different combinations to identify the impact of ion type and ion concentration on the wettability in the presence of and without acids in the oil. As rock, 2 calcite samples were used. In a later stage, the rock sample was conditioned in a dodecane solution with 1 weight percent pentanoic acid, which I will explain later. The measurement of contact angles was done with a high drop analysis system. On the left-hand side, we can see the setup of the device. It contains a reservoir for the surrounding brine, a capillary to inject the oil drop on the rock sample inside of the view cell. In this view cell, the contact angle can be measured with the camera connected to the analysis system after switching on the light. For the measurements, the rock sample was first cleaned with acetone and then placed inside the view cell. The cell was filled with brine and brought to 150 bars pressure and 60 degrees temperature. Then an oil drop was injected from the bottom and placed on the rock surface. Following, the intensity of the light and the angle of the camera were adjusted before the contact angle and the drop size was measured. During the measurement, every 5 seconds, a contact angle was measured until this angle got constant. Further, I also only included drops that had a size of around 25 microliters to exclude an effect of the drop size on the contact angle. For each brine, I conducted 2 or more measurements to reduce fluctuation effects. So in total, I did 6 experiments from which I will present and discuss the results now. In the first experiment, model oil 0 without acid compounds was used, and the calcite sample was cleaned with acetone between each measurement to restore the original state of the rock sample. Looking at the results, we can see that the contact angle increased with increasing salinity, which is in accordance with the literature. At 3% ion concentration, the rock is water wet for distilled water, the sodium and magnesium. The contact angles of calcium and sulfate are closer to 90 degrees and show a more neutral wettability. In the second test, with the ions at a concentration of 10%, the contact angles increased, such that all ions show a neutral or more oil-wet rock surface. This increase of the contact angle and the shift from water-wet to oil-wet at higher ion concentration is confirming the expectations from the literature. In the next experiment, model oil 0 was changed to model oil 1, which contains 1 weight percent pentanoic acid. However, the results from experiment 2 show little difference among the ions and the concentrations. As we can see, the contact angles decreased for the ions, showing a stronger water wettability. In context with the literature, a higher oil wettability was expected by changing to the model oil 1 containing acids. Only the calcium at 10% concentration marks out of the results and shows a tendency to neutral wettability. That especially calcium has this strong impact can be explained as calcite is made up of calcium carbonate, wherefore the calcium has a high tendency to interact with the calcite, reducing the partially negative charges of the carbonate further, resulting in a stronger positive rock surface. That the impact of calcium is thereby stronger than magnesium could come through the temperature effect on the reactivity. Calcium has a higher affinity to react already at lower temperatures, while magnesium becomes more reactive only at high temperatures. To investigate this striking calcium at 10%, I repeated the measurement in experiment 3 with the calcium at 10%, but this time using the backup calcite sample. And what we can see is that by changing the calcite sample, the measured contact angle increased from 76 degrees with sample number 1 to 124 degrees with sample 2. So by changing the rock sample, the wettability changed from water wet to oil wet. The higher oil wettability in experiment 3 confirms the literature and the expectations. This higher oil wettability with the calcite and the oil containing acids compared to the oil without acids was expected, as the negative surface charge of the acid tends to absorb on the positive surface charge of the calcite. This effect of changing the rock sample could indicate that a conditioning effect has occurred at sample number 1. A conditioning could have happened during the measurements or through the cleaning of the rock sample between the experiments, causing an increasing water wettability of the calcite surface. It could also indicate that the calcite rock surface is not generally positively charged, as believed in many papers, but that it is very much dependent on the distribution of the positive charged calcium and the negatively charged carbonate at the rock surface. To investigate now if a conditioning effect is the reason for this unexpected strong water wettability, I repeated the experiment 2, but this time the calcite sample was placed in dodecane with acid compounds for 64 hours to see if the water wetness will decrease. Despite the treatment, we can see that the rock stayed strongly water wet, but compared to experiment 2, the contact angles of experiment 4 for most ions slightly increased. I had to assume that the conditioning in oil could have only a small impact because of the cleaning of this rock sample with acetone before each measurement, or maybe that the acetone could be the reason for the strong water wettability. To test if the cleaning with acetone was the reason for the water wettability, I repeated the experiment excluding the cleaning with acetone. Instead, the rock sample was dried and placed in dodecane again for 15 minutes between each measurement. Looking at the results, we can see that removing the acetone from the procedure did not yield in an increase in oil wettability. As the wettability is still opposite of what is expected, the potential conditioning effect could only happen during the measurements. Thus, I had to assume that this repeated exposure of the sample to brine caused a continuous attraction of the rock surface to be coated with water. This could explain the increasing water wettability of the calcite sample with the number of measurements. In the last experiment, I increased the acid concentration in the oil to 5% to see if it will cause a shift in wettability. For the ions, only calcium and sulfate were selected, as they showed the most impact and represent divalent cations and anions. The contact angles measured show two findings. First, we can see that increasing the acid concentration increased the shift towards less water wet, which was already expected for model oil 1, but did not show, probably due to a conditioning effect during the experiments. Increasing the acid concentration to 5% shows this expected change. Second, the results also confirm that especially the calcium cation causes a stronger shift towards oil wettability, while the sulfate anion causes a stronger water wettability, which is both in line with the literature. Further, it also shows that the ion type is of greater importance for the wettability than the ion concentration, as for both ions, the angle at 3 and 10% concentration are similar. Coming to the conclusions from my observations. The first drawing is confirming the literature with regards to the effect of the ion concentration. Through the experiments, it could be confirmed that increasing the ion concentration in the brine reduced the water wettability of the rock sample. Still, it must be said that these effects during the experiment get reduced, likely through a conditioning effect. Second, the effect of the ion type was investigated. The results of the experiments show that the ion type has a higher impact on the wettability than the ion concentration. This result is underlined by analyzing the effect of the specific ions. It could be proved that the potential determining ion, calcium and sulfate, show stronger impact on the wettability than the non-potential determining ion, sodium, as it is reported in the literature. Hereby, calcium showed a stronger change towards oil wettability than magnesium. This is interesting as they are both divalent cations. However, the strong effect of calcium could be explained by the rock selection or the temperature as said before. Another explanation can be found in the literature, where stronger interactions of carboxylic groups, like the acid in the oil, with calcium than with magnesium are reported. Also, likely a conditioning effect during the experiments was identified, causing fewer clear results or results opposite of what was expected. The experiments 4 and 5 showed that the cleaning with acetone was not the reason for it, so it is likely that the reuse of a single sample and the repeated exposure to brine during the measurements caused an effect that increased the water wetness of the rock sample. This was seen in experiment 3, when the unused rock sample 2 was used with the same procedure from experiment 2 and showed a highly different contact angle that defined the sample as oil wet and not water wet anymore. After analyzing the results and reviewing the experiments, some recommendations can be given for repeating and extending the experiments. First, for a detailed investigation of the electric double layer, the setup potential must be measured, allowing the identification of the surface charges. By knowing the precise surface charge, the experiments can be closer linked to the literature. Attractive and repulsive forces, as well as the assumed conditioning effects, can be better investigated, and the charge of the surface could be eliminated as a potential reason for some unexpected results. A second recommendation would be to extend the alteration time of the rock sample in oil. As the carbonates in the reservoir are exposed to oil for thousands or millions of years, a strong oil wettability is establishing. In many publications, a placement in oil for several weeks or even months is reported to cause an effective alteration. However, due to the limited time for my master thesis, this could not be done. Related to the conditioning effect is also the usage of different but very similar rock samples. As it was seen during the experiments, the impact of ion type, salinity, and acid compounds reduced more and more, probably due to a conditioning effect of the sample used. This could be avoided or at least reduced by using different but very similar samples for the experiments that are all prepared in the same way. And the last recommendation aims to include other factors in the investigation. In this experiment, the specific ions were in the focus. In the next step, it could be investigated if not only the charge of the oil, but also different polar compounds in the oil cause different impact. And with this, I'm coming to an end. Thank you very much for your attention. I'm welcoming any questions, and I hope it will work.
Okay. So unfortunately, I've had a message from Mats. He's been called into safety training, and he is not here. So I would ask the judges, there are some questions that pertain to the question and answer session, so obviously they would score 0, but you can continue to judge the remaining that you feel comfortable doing so. But unfortunately, he has just withdrawn. which is a shame, very much a shame. However, we do have our next our next candidate. Almandir, can you hear us?
Yes, I can.
Fantastic. I'm about to start your presentation, but would you like to introduce yourself quickly to our audience here today? Oh, okay.
Sure.
Bear with us. Sorry.
Okay, so my name is Almandir Al-Jalili. I'm a student from Hiratwat University. I studied Master of Science in Reservoir.
Sorry, Almandir, if you can pause for just one second. The judges just need to review something. So we'll leave a gap after each presentation for you to finish. Thank you. Almandir, you are welcome to restart. My apologies for that.
No problem. So my presentation will be played, right? The recording.
Okay, are you happy for us to start?
Okay. Okay. So I guess I recorded the presentation. I'm sorry because I don't know the format of this presentation because I submitted a pre-recorded presentation.
Thank you.
I'm Almandir Al-Jalili, a student from Hiratwat University, and this is my presentation for the SPE Student Paper Contest 2023, which is titled Impact of Salinity on Water Flood Displacement Efficiency. So the outline of today's presentation is that we'll go through a background, first of all, followed by aims and objectives, then methodology, results, conclusions, and finally some recommendations. So, to start with, water flooding is a widely used oil recovery technique due to its efficiency and applicability. Moreover, fluid properties are among the main parameters that affect water flood performance. Salinity-related research is gaining increasing popularity where the studies are mainly focusing on low salinity water flooding. However, the majority of these studies involve geochemical reactions, while there is a lack of the physical fluid properties impact, which is one of the main objectives of this study. So the aim is to investigate when do salinity, temperature, and CO2 solubility make a difference to the sweep efficiency. This will be studied by the impact of injection of water of different salinities and lower temperature on oil recovery of with and without dissolved CO2. The focus will be mainly on the changes of the fluid physical properties, namely the density and viscosity, with no geochemical reactions assumed and modeled accordingly. So in terms of methodology, this study is mainly by numerical simulations, which is running sensitivities using the CMG GEM compositional model. There has been 12 water salinity cases created for 4 formation water salinity and 3 injection water salinity, which have been repeated over 8 system sets from 2D to 3D grids representing different systems, and the oil used is the light oil. In total, there has been 101 simulations performed and forecasted for 40 years to see the results. So this flowchart shows the complexity and different systems of this study, starting with isothermal system without CO2, moving on to the introduction of CO2 to the isothermal system, and then investigating the non-isothermal systems. And finally, having additional cases for further investigation, namely are mainly for the study of gravity effect. So this plot shows the main results of the study in terms of the oil recovery factor. What we can see here is that we have the different systems, the isothermal with and without CO2, and then the non-isothermal. And the columns represent the 2D and 3D grids respectively. What we can notice here is that the highest oil recovery factor is for the isothermal system with CO2, and that the values are 60.3 and 59.6 for the 2D and 3D systems. What we can notice as well from here is that although, as mentioned earlier, for each system there has been 12 cases, 12 salinity cases simulation for each system, here we can only see one value for the oil recovery factor, which means that for the 12 salinity cases for each system, there has been only one, or there has been the same oil recovery factor, indicating that salinity did not impact the oil recovery factor in this study. Moving on, to understand why we got these results and to dive deeper into the discussion and analysis, we'll start with the isothermal system without CO2. So here we have a plots on the right for the oil density and on the left for the water density. So starting with the oil density, the initial value of the density is 566, and we can see that the density is slightly decreasing with time in the producer side. And when we talk about the water density, especially in the injector side, we can see that the starting value is 972, and that the density of water is increasing with time. And one noticeable thing here is that the low salinity, low injection water salinity cases, which is the dark blue, has lower density compared to the higher salinity cases. However, this didn't improve or change the oil recovery factor, and the oil recovery factor for this system is 55.9. Moving on to the next system, which is the isothermal with CO2, what we can notice here is that for the oil density has increased compared to the previous system without CO2, which means that the introduction of CO2 is increased, has led to an increase in the oil density. And this increase is also, we can see it's increasing with time. However, when we compare the water density of the system with the one without CO2, then there's no noticeable difference. And also the introduction of CO2 into the system has made changes to the oil viscosity. Mainly it's decreasing the oil viscosity. So this combined effect of increasing the oil density and decreasing the oil viscosity has led to a significant increase in the oil recovery factor compared to the system without CO2. So here, further to understand the behavior more, this time in the non-isothermal systems, where the water injection temperature has been decreased from 100 degrees Celsius to 40 degrees Celsius. So on the right hand side for the oil density, we can see that the density are increasing in the injector sides, but for the producer sides, the with and without CO2 systems are more or less have similar behavior to the isothermal systems. But here the main effect is on the injector sides, and it's felt especially in the water density, as the water density has increased significantly from 970 to 1000 in the injector side. However, with all of these differences or effects on the physical properties of the fluids, the oil recovery factor hasn't increased a lot compared to the previous case, and that it's lower than the isothermal system. So to understand more about the different effects on the systems, here in this plot we see a salinity fronts, namely in the Na molality. So on the left hand side is a case with high injection water and low formation water salinity, and on the right hand side is the opposite. So what we can notice from this one is that the salinity is changing with time in both cases. However, even with this change in salinity, the oil recovery factor hasn't changed, indicating that salinity is changing, but their effect on oil recovery is absent. Moving on, here we see a comparison between the saturation front on the left hand side and the temperature front on the right hand side. So what we can see is that the saturation front is propagating in much faster pace compared to the temperature front, and that in this forecast date, which is 2020, which is half the forecast time and before the breakthrough, we can see that the water saturation is reaching the producer side, but the temperature front will not reach the producer side during the operational time of this well. This will lead to the thermal effect will not be felt in the producer side. This plot shows the oil and water viscosities, and it's mainly to understand the significance of the effects. So on the right hand side we can see the table of the oil and recovery factor and the mobility ratio, which both are calculated. So the oil recovery factor for the isothermal system with CO2 is the highest here, although the non-isothermal systems have a lower mobility ratio, which was expected to have a higher oil recovery factor. But here we can notice that the isothermal system with CO2 has a special phenomenon, which might be attributed to the phenomenon of CO2 in the oil, which is the oil swelling. Additionally, the introduction of CO2 to the system will also delay the water breakthrough, leading to this high oil recovery factor. And when we compare the isothermal system with the non-isothermal systems, we can notice that the oil swelling influences the recovery more than the mobility ratio when the system is isothermal. So this slide is about the additional cases or the additional investigation cases, which are mainly to see the gravity effects. So these two cases are based on the non-isothermal system with CO2. There has been, or for these cases, the system has been divided into two layers, the top and bottom, with 500 millidarcy difference. So the figures on the top is about the higher permeability layer at the top, and vice versa for the bottom cases, or for the bottom figures. So first of all, what we can notice here from the top and bottom figures is that there are some gravity effects, and this gravity effect is also augmented by viscous forces in terms of the bottom case, where the gravity will be, where the water will be driven by gravity toward the bottom. However, when we compare with two different times from the left to the right, we can see that the fronts are propagating in the same way and that the inclination is not changing, indicating that the front is stable, and this is mainly due to the low mobility ratio. So what we can conclude from this slide is that although there are some gravity effects apparent here, but the low mobility ratio has resulted in a minimized gravity segregation. And this is also seen in the oil recovery factor for the two different cases, and is that the oil recovery factor is almost the same. So, based on this study, there are the sets of the main conclusions. First of all, as can be seen before, salinity did not have an impact on the oil recovery factor, as all the variable salinity cases resulted in the same recovery factor. Also, CO2 increased the oil density and reduced its viscosity, while the effects on water properties are insignificant. Moreover, the reduction in temperature slightly decreased the oil properties and significantly increased the water properties. So the combined effect of temperature and CO2 is that the CO2 increased the oil recovery factor more than the reduction in temperature, as oil swelling appears to be more significant this time than the low mobility ratio in isothermal settings. Finally, gravity segregation was minimized due to the very low mobility ratio, leading to a stable displacement front. So the main outcome of this study and this conclusion is that ultimately brine tracking is not required, while temperature modeling is advised in a compositional simulators. So in terms of recommendations for further study, it's recommended to perform similar sensitivities that has been done here, but with different oil properties and compositions. Moreover, it's advised also to try and change the model size and properties to see the different effects of numerical simulations, as simulation effects play a key role in the results seen, almost in all simulation related studies. Moreover, also it's advised to combine the outcomes of this work in terms of the effect of physical fluid properties with the main effects, which are the geochemical interactions or reactions, to differentiate the significance of both parameters on oil recovery. Finally, it's also recommended to repeat the study for the impact of CO2 injection in saline aquifers. So this was my presentation. I hope that you enjoyed it. Thank you very much for listening, and I'm ready for any questions. Thank you.
Okay. Almadir, are you okay to receive questions for the judges?
Sorry, receive question from what?
Okay. Thank you for a very nice presentation. I have a question regarding the title of your paper. Why is the word salinity only written in the title, when in your paper you also showed the influence of CO2, temperature, and gravity on the recovery factor? At the end of the paper, 10 conclusions are stated, only one of which refers to injection water salinity. In that one statement, you written, injection water salinity didn't have an impact on oil recovery. Is it true because you modeled only influence on fluid properties without taking into account geochemical reactions? Thank you.
Yes, thank you for this question. So mainly the name was as stated by my supervisor, so I didn't change the name. And then in terms of the CO2 and the temperature, these components were added as we go throughout the study. So the first part was about salinity, and then when there was no main effect about salinity, we thought about adding the CO2 and temperature to see also the combined effects. So maybe the name is general, but in the end it can be edited, no problem. And the point about the geochemical reactions, yes, because it's stated that in the aims and objective of the study is that this study is about the physical parameters, the physical properties effects, because majority of studies are there in the academia related to geochemical interactions, but as I said, there's nothing really specific about the physical properties. So we thought we need to do a research in this area. That's why it's the conclusion is based on the fluid physical properties and not geochemical interaction.
Okay, thank you. You written at the end the recommendation to take into account both parameters on oil recovery. Thank you.
Yes.
Okay, Amadeo, thank you very much. Amadeo, thank you very much. There are no more questions from the judges, so thank you very much for your presentation.
No worries at all. Thank you very much.
Okay, thank you. Next, we have Ibrahim, the Imperial College of London. Can you hear me? Oh, yes. Just want to check this. Yeah.
Yes, I can hear you. Good morning, everyone.
Fantastic. Thank you. The judges are just reviewing the previous paper, so we'll be ready for you in just a moment. Okay, Ibrahim, would you like to introduce yourself before we start your video?
Yes, sure. My name is Ibrahim Al-Abaidan. I completed my master's degree in petroleum engineering last year at Imperial College London. I am very interested in reservoir monitoring and surveillance applications to improve reservoir characterization and formation evaluation. I hope that you will find my presentation informative. So if you can start my presentation, please.
Thank you. We'll start.
Hello, everyone. My name is Ibrahim Al-Abaidan. I am glad to have this opportunity to participate in SPE student paper contest. What I am going to present today was part of my master research project, which I completed last year at Imperial College London. My presentation title is Finite Element Modeling of a Knife-Based Microimager, Resolution and Depth of Investigation. In this presentation, I will go over a brief introduction of the topic and the purpose of this study. Then I will present the methodology and discuss the results. And finally, I will summarize with the key findings of this study. So what are microresistivity imagers, or simply microimagers? Microimagers are electrical borehole imaging tools used to measure the near borehole resistivity. These tools provide high-definition resistivity images that help to identify small-scale geological features such as thin beds and fractures. The measurement principle is highly dependent on the drilling fluid used, either conductive or resistive drilling fluids. For resistive drilling fluid, the challenge is to maintain electrical continuity between the tool and the formation. This is because the non-conductive mud along the borehole wall will act as a high resistive layer, restricting the electrical current flow. To tackle this issue, one of the available technologies is called knife blade technology, shown in this figure. This technology uses electrodes designed as knife blades that cut through the mud cake, creating a direct contact between the tool and the formation. Like other microresistivity imaging tools, this tool can be characterized by its borehole coverage, resolution, and depth of investigation. Compared to other types of microimagers, there has been no previous work to characterize the knife-based imagers in terms of resolution and depth of investigation. Understanding these characteristics helps in post-processing and data interpretation. Also, it helps in identifying areas for future tool improvement. So the objective of this project is to investigate the synthetic tool responses of the knife-based imager introduced in 2016 by Weatherford, and to determine the characteristic of this imaging tool in terms of vertical resolution and depth of investigation through 3D modeling. This slide shows the main contributions from a previous work published by several authors. In this literature review, I looked at the measurement principle of the microresistivity imager tools, as well as applicable methods to determine imaging tool characteristics through 3D modeling using finite element methods. To simulate the tool response, we need first to understand how the tool measures the near borehole resistivity. This figure shows the imaging pad of the investigated tool with 10 electrode plates. To measure the resistivity, one electrode plate acts as a current electrode and another acts as a voltage measurement electrode. From the injected current and the measured voltage values, we can calculate the near borehole resistivity using this equation. The K factor in this equation is a multiplier that is dependent on the geometrical spacing between electrodes. In this method, the measurements are taken across different electrodes in sequence. I use a finite element modeling software, COMSOL Multiphysics, to generate the tool response using a 3D model of the imaging pad. By considering the resistivity of the model, the software solves for the electrical potential in the measurement electrode by modeling the injecting current from the current electrode. This was done by solving the continuity equation for the electrical potential based on Ohm's law. The software uses a 3D mesh to compute solutions of the partial differential equations. The technique that I use for meshing called physics control meshing sequence, which creates a high resolution mesh based on the physics used in the model. This workflow summarizes the modeling process that I used to construct several resistivity models. Those models were used to simulate thin beds responses, electrical penetration, and mud invasion response. In constructing the resistivity models, the following assumptions were considered. All imaging electrodes cut through the mud cake into the formation, basically no tool standoff. There was no need for mud cake correction due to electrode design. and the modeling of the direct current resistivity was sufficient to assess the tool responses within a predefined resistivity range from 0.2 to 100 ohm, and the effect of temperature on electrical resistivity was not accounted for in this study. Now let's go over the modeling methods, starting with thin bits modeling. Here we have two 3D layer cake resistivity models to generate the thin bit responses. The single bit model includes a high resistive bit in the middle with certain bit thickness, whereas the multiple bits model includes multiple resistive bits with increasing bit thickness. Several variations of these models were constructed with different thicknesses and resistivity contrast. These models were used to identify the minimum vertical thickness the imaging tool can distinguish. Here we have the single and multiple bits responses. The y-axis is the depth along the borehole in inches, and the x-axis is the resistivity in ohms meter. For single bit responses, the resistivity contrast is 1 to 10 with increasing bit thickness from figure A to D. We can clearly see that the tool failed to detect the resistive bit in figure A. However, the resistive bit is clearly distinguishable and follow the true formation resistivity in figure B, C, and D. This is true even with the presence of shoulder bit effect. In addition to that, the error in the measured resistivity is significantly reduced as the bit thickness increases. We also tested the tool across multiple parallel bits with two resistivity contrast, as we can see in figure E. Like the single bit response, the tool was able to detect the resistive bits. However, bits with higher resistivity contrast can be detected easily. Moving to electrical penetration modeling, this model includes two resistivity contrasting bits with certain dip angle. The model was used to compute the electrical penetration length, which is the radial distance into the formation when the tools reach the square root of the resistivity above and below the dipping interface. In this method, the DOI is taken as the average EPLs from different dipping angles and resistivity contrast. Here we have the synthetic responses to 30 and 45 dipping angles with different resistivity contrast. The x-axis is the vertical position along the borehole wall in inches, and the y-axis is the resistivity in ohms meter. From the dipping angle and vertical distance, the electrical penetration length was computed for each resistivity contrast. The values are summarized in this bar chart for one electrode pair. Same procedure was done for other electrode pairs, and the average EPLs are summarized in this table. Using statistic, the DOI is taken as 0.6 inch from this method. Moving to mud invasion modeling, this model was used to simulate a resistive mud filtrate invasion by varying the invasion radius. From the resistivity response, the pseudo-geometrical factors can be computed for each invasion radius as given in this equation. Rxo is the resistivity of the invaded zone, and RT is the resistivity of the non-invaded zone. The depth of investigation is defined as the invasion radius at which the signal is equal to the average of the resistivity of the invaded zone and non-invaded zone. That means when the pseudo-geometrical factors equal to 0.5. The first graph in dark blue shows the resistivity response as the invasion radius vary from 0 to 5 inches. The resistivity of the invaded zone is 100 ohm meters and the resistivity of non-invaded zone is 10 meters. This ratio was chosen to simulate a resistive mud filtrate invasion. As the invasion radius increases, the tool starts to read the resistivity of the invaded zone. From this resistivity response, I calculated the pseudo-geometrical factor as shown in the second graph in red. The DOI is defined as the invasion radius when pseudo-geometrical factor equal to 0.5 as explained earlier. As a result, the DOI is 0.625 inch from this method. Same procedure was done for other electrode pairs. However, there was no difference in the computed DOI. Here I have summarized the key findings of this study. The vertical resolution obtained by modeling is 0.5 inch. The estimated error in the measure resistivity is 3 to 11% for 2-inch pitch or thicker. The depth of investigations obtained are 0.6 inch and 0.625 inch from two different modeling methods. There is a significant reduction of shoulder pitch effect for pitch thicker than 0.5 inch. There is no significant difference between the imaging electrodes in terms of resolution and depth of investigation, and the asymmetry above and below the imaging electrodes has a slight effect on the tool response. In conclusion, this paper investigated the synthetic responses of a knife-based microimager deployed on resistive drilling fluids. The resolution and depth of investigation were determined for the investigated tool, and the results can aid in improving the evaluation of geological features. Also, it can be used as a benchmark for future tool development. The study in general can be used as a guide to simulate synthetic responses for other microresistivity imagers based on 3D modeling. This brings me to the end of my presentation. I would like to thank my supervisors, Professor Matthew Jackson from Imperial College and Dr. David Fu and Benjamin Treadgill from Weatherford International for their help and support throughout this project. Thank you for listening, and I would be happy to answer any question.
Thank you very much, Ibrahim. We will now take some questions from the judges. Go ahead.
Do we hear each other?
Yes, I can hear you.
Okay, Ibrahim, congratulations on your presentation. And at the beginning, just a small advice. According to the rules, you should apply only SE units, but in petroleum engineering inches are also welcome, but just for your future work to be advised. So I have only one question. As you explained us, you investigated several FEM which were designed according to three methods: fine beds, electrical penetration, and mud invasion. And that scenarios of blades, electronic blades, are cutting through any present mud cake. So you wrote in your paper that in the future that it can be expected that you do the similar work when electrode blades should partially cut through a mud cake. Can you tell us what novelty can you expect according to your results shown here, and what do you expect from the results in the future when partially cuts should be applied?
Yeah, so for this work, or for determining the resolution and depth of investigation, what have been done is fairly enough. However, if we are going to consider the use of images or resistivity imaging and fracture characterization, we need to really know, is this response from let's say ideal situation, or we have like some of intervention from other for example from mud. For this reason, we can expand this work to consider that scenario. But for the purpose of this paper, yeah, that what have been done is fairly enough.
So better response in diameter of investigation could be expected even if,
Yes, this will affect definitely the response. So maybe because, as you know, if we have like isolation or something that will prevent the signal from going into the formation and return, that will affect the accuracy of the signal or the measurement itself. So we will expect higher error or bigger error in the measurement.
Okay, thank you.
Any other questions from the judges?
Hello, thank you for the presentation. The device that you used in your paper and made your this model on, do you know the actual accuracy of the device? And was the assumption that the temperature has no effect on this model that you created? Was that your assumption, or is it because it's a smart device?
Thank you for the question. So we don't know the exact characteristic of this imaging tool. However, we know the previous generation, which was introduced in 2007, I guess. So for this device, we don't know, but we know a range of values for such tools. And for the second question regarding can you repeat the second question, please?
In the assumptions that you put on the, I think it's third or fourth slide, you said that the temperature has no effect on the measurement. Was that your assumption, or is it because it's because of the characteristics of the device, because it is a smart device?
Yeah, thank you. Usually when we model resistivity response, we don't consider the resistivity, we don't consider the temperature variation, because that has a negligible effect on the modeling process or in the results. So even if we think that we need to consider it, we can include a correction factor later on. But usually for resistivity modeling, we don't need to consider the temperature variation. I hope this answered your question.
Okay. Thank you very much, judges. Thank you very much, Ibrahim. That's all the questions from our judges. And congratulations.
Thank you very much.
Hello, Alan. Good to see you. We're just going to give the judges a few moments to review the previous paper, and then I'll ask you to introduce yourself.
Sure.
Okay, Ahmed, the judges are ready for you now. Before we play your video, would you like to kindly introduce yourself to our judges and audience?
Yes, sir. Good morning. My name is Ahmed Al-Ajnaf. Just graduated from the University of Manchester, studying subsurface energy engineering. I really hope that you enjoy my research today. And unfortunately, I couldn't come today since I'm in a completely different continent, so it's quite difficult to get here. But I really hope you enjoy my work. Thank you.
Thank you very much.
Hello everyone, my name is Ahmed Al-Ajnaf from the University of Manchester, and today I'll be presenting the topic salt precipitation during carbon capture and storage in a saline aquifer. So what we're going to go through today is, first we'll go through how salt precipitates in a saline aquifer, then I'm going to talk about the importance of salt precipitation. After that, I'll briefly go through the methodology I use to study salt precipitation. Then we'll move on to the results and analyze graphs so you can see where the salt precipitates within the formation, and then I'll end it with a summary. So let's start. When CO2 is injected into a saline aquifer, over a period of time, 3 zones start to develop, which are Zone 1, the dry out zone. This is where a massive accumulation of salt is present, usually near the injector. Zone 2 is the two-phase zone where both supercritical CO2 and saline water are present. And finally, Zone 3, the saturated zone, where only saline water is present and isn't affected by the CO2 injection. Let's dive a little bit deeper. The precipitation of salt happens in Zone 2, and let me explain why. As the supercritical CO2 is pushed within the formation, it will displace the saline water until it reaches irreducible water saturation. However, this displacement causes a pressure difference between the supercritical CO2 and the saline water, which is known as capillary pressure. Since CO2 is continuously injected into the reservoir, it should be expected that the pressure of the CO2 to be greater than the pressure of the saline water. As a result, the saline water from Zone 3 will try to fight back and push into the two-phase region, which is a mechanism known as capillary backflow, which is similar to the capillary pressure. Since the capillary backflow is a continuous cycle just as the injection of CO2, the pushed saline water from Zone 3 to 2 will eventually evaporate, which creates the precipitation of salt. And over time, these salts will start to accumulate and stay within the pores. Now, why is this important? Well, first let's define the precipitation of salt as an equation, which is shown on the slide. Here, the Sg is the average gas behind the dried zone. We have the two densities for both saline water and salt, and we can see that the salt precipitation is related to how saline the water is. As more and more salt begin to precipitate within the rock, the pores begin to decrease. And this is because the salt particles get clogged and get stuck in the pores of the rock, which results in the porosity to decrease. And this is critical, as this means that there is less space for the injected CO2 to travel within the formation. And we can calculate how the porosity reduction is by the equation shown in the slide. Now, since there's a decrease in the porosity, then the next parameter that is affected is the permeability. And this is because there is a direct relationship between the permeability and porosity. And this is shown in the equation on the slide, which is the Cosny-Kármán equation. The permeability can be defined as how easily a fluid can flow within the pores, which in this case would be the CO2. And if there's a decrease in porosity, then we should expect a decrease in the permeability, which means that it would make it harder for the CO2 to migrate within the formation. And we can take this a step further and bring in Darcy's law, with the equation shown on the slide. Now, for CCS, companies would want to keep the injection constant because they could have a specific injected volume they want to target, whether it is to reduce carbon tax emissions or to contribute to net zero. The area, viscosity, and length are all constants, which leaves us with only the permeability and the pressure changing. So if we rearrange the equations to solve for the pressure, we can see that a decrease in permeability will lead to an increase in pressure. And that's just trouble. If the pressure is continuously increasing, then the likelihood of reaching fracturing pressure is high, which means you will damage the formation, lose the integrity of the caprock, and more. So, what's the current landscape for CCS in saline aquifers? Well, first, there's currently 6 operating projects to this day, with over 20 planned for the near future. Methyl ethyl glycol is the current solution to mitigate salt precipitation and is currently being used in the Snovovid field. And finally, if you want to study salt precipitation, you can use commercial softwares such as Tuf2 and CMG Gem, which costs quite a lot of money to install in just one computer. Now, essentially, what this project will bring to this field of study are the following. First is to study various sensitivity parameters that might affect the salt precipitation, such as injection rates, heterogeneity, salinity, and more within the future. Second is to create an interchangeable model that can be used not just for saline aquifers, but for depleted oil and gas reservoirs or even producing oil reservoirs. And finally is to create something that is accessible for students and academics to study CO2 storage and salt precipitation without the need for expensive commercial softwares. And for me to achieve all of this and to study salt precipitation, I developed a reservoir model on MATLAB using MRST, which stands for MATLAB Reservoir Simulation Toolbox. And the best way to describe MRST is, as the name implies, it's a toolbox that contains many features associated with reservoir simulation, such as generating grids and solvers like black oil that is commonly used in petrol. But it's not a standalone simulator. It's not interactive and simple. It involves a lot of understanding and heavy coding, and it's my job to pick up the tools and build the model from ground up, from creating the grids to placing the wells to injecting CO2 and everything in between. And the one thing I did the most throughout the whole research project is debugging, constantly just fixing lines of codes just to make sure everything fits perfectly and is fluid, and the end result is creating this model. I validated the model through literature before jumping in, and the model is based on the Snovovid CCS field mentioned previously. And essentially, the model will generate a number of figures, such as CO2 migrations and fluid zones, salt precipitation locations, and effective porosity and permeability, and so on. And I'll be using this to analyze different parameters such as injection rate, homogeneous versus heterogeneous permeability, and salinity. So let's take a look at the base model a little deeper. So here we have the CO2 migration on the left and the fluid zones on the right. It's important to note that in the fluid zone figure, anything beyond the blue area here is just the saturated zone, meaning just saline water. And of course, the mixture of color in the middle is the two-phase region, which is where the precipitation of salt ended at the time of simulation. The second figure was made to help visualize where the location of salt precipitation is happening at the time of simulation, so you can use that as a reference. And we can move on to see where the salt is present within the model. Both figures represent the salt precipitation, and if you run the code, both will generate. I personally favor the one on the right, as it shows a better representation of the salt precipitation. And we can see that there's a lot of salt accumulation at the bottom of the injector. And if you go up from the accumulation, you see the yellow shows that there's more precipitation of salt next to the well, which is something to be expected. And if we show the porosity and permeability, you can see the zones that are affected. As expected, the zones that are significantly affected are where there's a massive salt accumulation. And if you look at the permeability grid, for instance, the original permeability was 750 millidarcies, and at the bottom of the injector, it reduced to about 470 millidarcies, which is just a significant decrease in terms of value. You probably noticed that there's more grids affected on the top of the reservoir, and that's simply due to how CO2 migrates. Due to buoyancy, the CO2 will favor going to the top of the reservoir and then travel laterally across the caprock, which as a result affects the properties over a period of time. Moving on from the base model, let's jump into the first sensitivity parameter, which is injection rate. So what you see here are the location of the salt precipitation within the reservoir for the two models. and we can see that there is a significant difference between them. For the low injection rate, the CO2 migration is near the injector, which leads to a massive salt accumulation surrounding the injector well. Overall, there is less salt precipitation within the model. However, this salt precipitation around the well isn't favorable, as it would stop the injected CO2 to migrate any further. As for the high injection, the salt accumulation is at the bottom of the reservoir, and compared to the base model, it's a little lower. Overall, there is more salt precipitation within the model, and that is due to more CO2 being injected. However, we can clearly see that there is little salt precipitation surrounding the injector well itself. And this salt accumulation leads to the reduction of porosity and permeability of the reservoir. So what we have in these tables, the top is the change of porosity compared to the base model, and the bottom is the change in permeability. When we look at these tables, the numbers suggest that the low injection rate has the less overall reduction in the properties. However, it is important to note that even though there is less porosity and permeability reduction for the low injection, the issue is that there's a significant salt precipitation surrounding the injector, as we've seen previously. This issue will cause problems with long-term CO2 injection and mobility within the reservoir. While for the high injection rate, the formation has more porosity and permeability reduction. The base model has the best overall ratio reduction within the formation and surrounding the well. This analysis raises the question of what would be the most optimum rate for CO2 injection within the saline aquifer, which is a question that can be answered in future work. Next, we have the heterogeneous permeability, where there are two different types, high, medium, low, and low, medium, high. And it's interesting to see how the CO2 migrates differently between the two cases. When you look at the salt precipitation graphs, you can clearly see the CO2 travel further in the high, medium, low formation because of the more salt precipitation. But even the low, medium, high CO2 migration is better than the homogeneous base model. In terms of salt precipitation, the high, medium, low model, the massive salt precipitation is deeper, but you see very little salt precipitation all around the injector well. What you do see is more precipitation further in the formation, and overall more precipitation compared to the low, medium, high model. As for the low, medium, high, there is more salt precipitation around the injector, but less salt precipitation overall within the formation. Moving on, we have the reduction of porosity and permeability of the reservoir shown in the tables. We can clearly see that the heterogeneous models have significantly less property reduction compared to the homogeneous model. This signifies the importance of considering a reservoir model's heterogeneity. For the high, medium, low model, both properties are more heavily affected by the presence of salt precipitation compared to the low, medium, high. For both models, the top layer of the formation is affected the most in terms of number of grid blocks, and it raises a question about how this will affect CO2 trapping over a more extended period of time. Next, we have the effect of salinity. The figure to the left is the low salinity, and to the right is the high salinity. The reason why the low salinity is shown in the grid form is because the magnitude is to the 10 to the minus 3, which is significantly smaller compared to the base and high salinity models. This shows the impact that salinity has on salt precipitation. When we look at the high salinity model, it can be seen that there is an immense amount of salt precipitation compared to the low salinity model. The injector well is surrounded by a massive accumulation of salt, which is more severe than the base model. This suggests that in the case of a high saline formation, if there were no mitigating procedures to reduce the salinity of the reservoir, then the objective of sequestering CO2 becomes difficult. As we can see, there is less CO2 injected within the formation because of the accumulation of salt that is blocking the injector. A high injection rate approach might be the best option. The rationale behind this is that if the injection rate is not high enough, then the CO2 will not be displaced faster and deeper into the formation, and this will reduce the salt surrounding the well. Finally, we have the porosity and permeability reduction for the salinity parameter. It is clear that the low salinity model for both porosity and permeability reductions are minimal, with very little percentage difference from the base model. When comparing this to all other models, low salinity keeps the properties of the formation close to the original value. However, at the same time, it shows that no matter how low the water salinity is, there will always be a reduction of porosity and permeability. As for the high salinity model, the porosity and permeability reduction values are immensely smaller than the reduced base model values, with a percentage difference of around 20% for porosity and 70% for the permeability. The salinity effect opens up the discussion to explore new methods of mitigating soil precipitation. A pre-flush of saline water before CO2 injection could be a solution. However, a water alternating gas approach, similar to the EOR method with water as low saline, could potentially improve CO2 migration and minimal soil precipitation. This would have to be thoroughly researched for future work. And now we have reached the end of the presentation, so let's sum up everything. I developed a MATLAB model to help analyze any CCS project with the addition to the effect of soil precipitation, which opens the gate for an accessible academic tool to help understand CCS more. Soil precipitation leads to a reduction in porosity and permeability. We've seen from the results that high injection rates cause less soil precipitation around the injector well, but more overall soil precipitation. Low injection rates has less overall soil precipitation, however massive soil accumulation around the injector. CO2 migration and soil precipitation favor a heterogeneous permeability compared to a homogeneous formation. A low saline reservoir has minimal effects on the reservoir properties, while a high saline reservoir leads to a significant soil precipitation with difficulty for the CO2 to migrate. Some future work to follow would be to analyze the optimum injection rate and to implement a solution to water alternating gas where we inject low saline water and then CO2 gas. I would like to take a moment to thank Dr. Vahid Niyasar for being my mentor for this research project, and I would also like to thank the SBE student chapter at the University of Zagreb for all their effort for hosting the student paper contest. Here are the references that were used throughout the presentation, and thank you for listening. I'm ready for any questions.
Thank you very much, Shannon. We'll now take some questions from our judges.
Thank you, Ahmed, for the presentation. Actually, you've answered all the questions that I prepared for you, but because my question was, have you considered and what do you think would be a possible solution for prevention of salt precipitation? And you mentioned WAG, but can you tell us, in that case, if we use pre-treatment with fresh water, what could be possible challenges in that case?
Thank you for the question. I think if it's when it comes to pre-treatment of water, for this instance, for a saline aquifer, I think the question has to be, how many times are you gonna flush the reservoir? Trying to push away the saline water, and at the same time, are you gonna produce this saline water that you're trying to push away from the injector? So are you gonna drill a well and produce it at the same time? And the question is, even if you pre-flush, how significantly will it affect the rest of the reservoir? You might reduce the CO2 soil precipitation around the injector, which is a massive problem within itself, which is a good idea. However, you have to understand that maybe doing it as like a alternating gas approach, where you constantly inject water within a 6-month period, or even a yearly period, it depends on the company and how the research goes, that you would want to reduce soil precipitation throughout the whole reservoir as a total, as much as you can. Because at the same time, you can see when we reduce the porosity and permeability through soil precipitation, the pressure is definitely going to increase. And you don't want to damage that caprock. You want to keep everything within the ground. And the question of pre-flush is, how many times are you going to do it after the initial stage? So, of course, it's a great idea, but companies have to keep in mind of the future dangers that might occur.
Thank you. And there is also a question of the amount of water that you need, and it's a fresh water. Of course, the pressure of the injection regarding the fracturing also. So thank you.
Any more questions? Okay, thank you very much, Ahmed. That's very kind of you. And we will leave you now and invite our next presenter to come and speak. Thank you very much.
Thank you.
Okay, so while our judges are preparing, our next speaker is in person. So we'll just get this presentation set up. Present for your laptop?
Oh, no, from here.
I think we can change the setting. I think we should be able to.
Yeah, that's amazing.
Is there a way to? It's like a.
Just skip it.
It's grayed out, so I don't know if there's a way to split the screen rather than watch it.
It's usually the it's something here and then screen right. This maybe.
I've just pressed that button
To hide.
It's
fine. I don't know. I can survive.
We've got time while the judges are preparing.
Yeah.
Oh, sorry. So
I will end it real quick because it's usually oh yeah, because the presenter yesterday was yeah, I have no idea.
no, it's fine.
Right, so if it's like this, and then presenters yes.
Yeah, but it's just duplicating the screen. So
Okay, all right. Yeah.
one second, let me just try one more thing. It doesn't seem to be picking it up as a separate one. But, let's try this. Sorry. So this one's moving forward.
Yeah.
There you go. So I think we're ready here if the judges are happy to begin. Perhaps you can introduce yourself before we start the
Hi everyone, my name is Jakub. I'm originally from Poland, but currently I'm studying in the University of Denmark, and I'm living there for 2.5 years. I would like to present part of my research regarding application of bio and bio-based surfactants as emulsifiers for the stabilization of water input oil emulsions. The research in the beginning was part of my master thesis that I did to graduate University in Krakow in Poland. So in the beginning, as oil industry, in average, we are producing 5 times more water than we are producing oil during the whole lifetime of reservoir. And this water may come in many forms. It can be free water, but sometimes it can occur as emulsions. The emulsions are not being made spontaneously. They are not created in reservoirs. They need some external factors, energy, like subsurface pumps to mix with water, on presence of naturally occurring surfactants and asphaltants in oils. We have 3 types of emulsions. One of them is water in oil, where water is the minor part, is dispersing oil. We have oil in water and multiple emulsion complexes when you have water in oil in water. My case regards water in oil emulsions. Yeah. So why the emulsions are an issue? Water, the presence of water is an issue. When we want to transport oil, there is a risk of corrosion caused by the water in the pipes, in infrastructure, and in refineries. And also it can separate spontaneously due to gravity differences. So we want to get rid of the water from oil before we transport it to refineries. So we have a few main ways how to do it. The 3 cases that I'm dealing with are first thermal, which is using decreased temperature. And when you are increasing temperature of surrounding, you increase temperature of oil, you decrease viscosity. So the oil becomes more liquid, more movable. It tends to move faster and it allows gravitational powers to work. Then we have chemical methods that are working by adding chemical compounds. Those chemical compounds can have either hydrophobic or hydrophilic parts, or both of them, which are dragging oil droplets or water droplets together and alongside. And we have also thermochemical methods, which is combination of both of them. We are adding chemicals and we are increasing temperature of the oil. So while decreasing viscosity, we are allowing the chemicals to mix easier with oil and water and to to work faster. There are 3 main methods of separation. It's a mechanism, sorry. So first of them is creaming and sedimentation, and the third one is population. In my case, it's going to be creaming. Creaming is based on the gravitational difference of action of gravitational forces. So oil. So every reservoir is different. There's no 2 same type of oils in the world. So every treatment needs individual approach. I was given oil from oil field in southeast Poland in Jastrzęb. It's light oil. It's chalk boundary of the light oil classification, and it's very universal. I wanted the oil to be as universal as possible, nothing special, nothing too heavy, nothing too light. Yep. So materials used for demulsifiers. So demulsifiers already exist. They are using heavy chemicals and chemicals that are not very friendly to environment. It costs a lot to produce them. And there is an issue what to do with the polluted water with those chemicals after separation. So I did some research about the natural compounds, and I chose 5 of them. All of them are widely used in the beauty industry. They are being used for shampoos and for face creams, and 4 of them are liquids, and the 5th one of them is dried root of soapwort, which my mother is using as washing detergent. So it actually works for us. So the methods, how they work. So an example of saponins that are presented, they have hydrophobic and hydrophilic parts. This part is hydrophobic tail that is pushing water out from the oil droplets and allows oil droplets to combine in the bigger flows and then allows it to be separated by gravitation. So all the biosurfactants were based for the emulsifiers. I used them as a base. I used 5 grams of liquids mixed with 30 milliliters of the water. And when we went to Sopot, I extracted 11 grams for 100 milliliters of water, and I basically cooked them. Then for each demulsifier, I created 8 samples with different amounts of demulsifiers. First I mixed water with the oil. There was 40% of water and 60% of oil in every sample. I was trying to make them manually by shaking the samples, but I realized that you cannot have the same sample, the same mixture with hand shaking because the process would be different. So I was supported by rotary agitator and with specially designed for tip for spinning that was designed for stabilization of emulsions for transportation. So to make sure that my emulsions are chemical stable, I decided to use this rotary tip. Creation of every sample of emulsion took 10 minutes with 1,000 rotaries per minute. So in total 10,000 rotaries. And then I manually mixed the emulsifier with the sample and shaked it. So I conduct the research in 3 temperatures. The first of them is temperature of surrounding, which was approximately 20 degrees room temperature. Second temperature is enhanced temperature of 40 degrees Celsius, and the third one is 60 degrees. For achieving the temperature, I use steam bath with hot water. And instead of pure or distilled or tap water, I used brine because I wanted to make environments of the emulsion as close to reservoir conditions as possible. It was 30 grams per liter NaCl. So first emulsifier tested was Sopot. In tests of room temperature, there was no separation. That leads to us to acknowledge that those emulsions were chemically stable. For 7 days, there was no separation of water and oil. Then in the temperature of 40 degrees, we can see that in every sample with the emulsifier, there is a total breakdown of the emulsion. 100% of the water was separated from the oil. Just a sample without the emulsifier, which is marked on blue as 0 milliliters on the bottom, there was no breakdown. Even though temperature was enhanced, but chemical was not added. So the emulsion is chemically stable even in increased temperature. But when we go to temperature of 60% in the middle graph, we can see that there's no total separation in every case, even though the emulsifier was added. So it leads us to the last graph that is explaining the amount of the emulsifier, the range of the emulsifier was working. As I mentioned in the beginning, the surfactants naturally occurs in the oils and they are responsible for stabilization of oil. If we add them too much, they are improving stabilization of the mixture. If we don't add enough of them, the mixture won't break down. But there's a small range between the amounts that we can apply and it's going to work as the emulsifier. So in this range, it's marked as a top peak on the last graph. So we can basically design the amount of the emulsifier that is working most prominently for each sample. So we don't have to add huge amounts of the emulsifier to work. We just need to find the range that is working. In second emulsifier base of glucoside, capryl, the total breakdown occurred in every sample with the emulsifier, and again, no separation in sample without emulsifier. Coconut betaine also work in every case in both temperatures for every sample with emulsifier except the one without the emulsifier. The same situation comes with rifats, except here we can notice in the 40 degrees that in the sample that has a smallest amount of the emulsifier added, there's no total breakdown. It leads us to the conclusion that the amount of applied emulsifier was not high enough to allow us to receive to get the 100% of breakdown of emulsion. And in the last biosurfactant base, lauroglucoside based emulsifier, we can see the total breakdown in every sample with emulsifier except the one without. So I wanted to compare bio-based emulsifier with commercial one that is already used in the industry. So we can see that even in the sample with small amounts of the emulsifier, it is working, but it's chemically based. It's not green chemistry. It's not environmental friendly, but it also works. So to sum up all of the demulsifiers I use, I choose the most prominent one, the one that allows the fastest breakdown in both temperatures, and combine them on the slides. So we can actually notice that the amounts of other demulsifiers have no impact. It's an active compound, and the range of applied demulsifier. And on the top left picture, we have samples after 7 days in room temperature. Separation, there is no separation, so they are chemically stable. And on the right side, we have the outcome of the test conducted in 60 Celsius degrees, and we can see the total breakdown of emulsion in every sample that the emulsifier was added, except the one without it. So even when the temperature was enhanced to 60 degrees, but the chemicals were not applied, there is no separation. So based on the entire research, we can notice that temperature has an impact on process of breakdown of emulsions, and added chemicals also have it. The range and amount of added emulsifier leads us either to breakdown of emulsion or to even increase stabilization of emulsion. And the main conclusion is that the bio-based chemicals, green chemicals, can compete with the chemicals that are used in industry, and they have positive environmental impacts, and they can replace them. Also, they can compete when it comes to the cost of production, because they don't require heavy chemical mixture compounds and energy-consuming processes. That would be all from me. Thank you for your attention.
I can be loud enough because this is not the correct solution. Yeah.
Thank you. Thank you for your presentation and work. It was very interesting. My question is, I guess you didn't do it, but did you, when you researched the subject, did you come up with information about actual toxicity and biodegradability of the product that you use? Because if something comes from the nature, it doesn't mean that it's not, toxic.
So they are. I know. I was going to say. Regarding the toxicity, some of them are not 100% biodegradable, but for example, support, which is my favorite, it's 100% biodegradable. I had issue with that because when I was conducting the tests, it started to get mold after 2 days in the temperature. So this one and glucosides, they are biodegradable, but refats and coconut betaine, they are not 100%. They need treatment, but the treatment is not as aggressive as treatment of other chemicals. So yeah, they are not all 100% degradable, but they are more biodegradable than the commercial chemicals used.
And did you do the analysis or come up with the data about it?
Yeah, so I actually bought all of the products in the shop, and I went to technical information about them that I provided, because under the EU regulations, every chemical sold must be provided with also technical data with all the compounds and information about toxicity, because as I mentioned, they are used in the beauty industry. So it's required for that. So yeah, I actually went through all the PDFs with information and checked it.
You considered, it's very interesting, that's why I'm asking you. You said, you mentioned the brine that you used and mixed it with oil. And you said it's synthetic, you prepare it in the laboratory. Or did you get the real samples from the field?
No, I actually made it in laboratory. I just mixed distilled water with NaCl. On the beginning, I was planning to use tap water, but in the city that I was doing, we are adding chlorine and other compounds to the water, so they would interfect the research. And also I decided to use salt water because it's debatable thing. There's many researchers up against and pro. They say that in some point salinity is increasing the emulsion making, and some of them say that it's decreasing.
And what was the salinity of the brine? I don't know whether you mentioned it or not.
It was 30 milligrams per liter.
It's quite high.
Yeah.
Why did you use such a high salinity? Because it's not an average. As you said, we wanted to have an, I don't know, as you said, average oil, not, you know, the light, not too heavy. And then you use brine, which is, you said it's 10%. It's quite high because it's usually much lower. It's up to, I don't know, 20, 25%, something like that. Because 30% is like an aquifer. It's not, you know, it's not usual to produce brine with such high salinity, and salinity stabilizes the emulsion. That's why I think maybe you should use a little bit lower.
Yeah, so about that, so as I mentioned, you say that it's stabilized, and some other researchers say that it has no impact. So I actually, before I chose the concentration of salts, I used pure water, distilled water, then I used 10 grams of salt, then 20 and 30, and there was no difference. So I just stayed with the last part for very easy reason, is because my technical guy from laboratory already made the whole jar of it for me, and it was enough for the whole. And I decided that in my case, I haven't noticed any impact of salinity on emulsion. So I just decided to go along with this one. But yeah, I'm very curious about the salinity impacts, but I couldn't find a straight answer, and I found very contradictional answers. So yeah, I just say that I understand it's very salty. Yeah.
Okay, if you're looking for the answers, you should not only consider the emulsions or water and oil emulsions that are formed during the production, but also the big problem with the emulsions, and that's why I'm asking you these questions, are the emulsions that are created during oil spills. And most of the oil spills, they happen in saline environments, that is oceans. And there are some scientific, research made on the impact of the salinity, and actually they prove that salinity actually stabilizes these emulsions. And my question is, do you consider that maybe in future, of course, the emulsifiers that we use today, they have the environmental impact, and we're talking about these bio ones. What would be, in your opinion, the biggest challenge of using these bio ones for the solution of the forming of the emulsions, which are the biggest problem when oil spills occur in the future?
Well, when it comes to the oil spills, it also depends on the regulations. Like in Northern Europe, we have regulations conducted by OSPAR, and they are very light. So we are just discharging water, but in more strict environments, it must be tested the impact of the water with biodemulsifier after separation. I think if the research is conducted about it, because I'm not biochemical, I don't know a lot about that, and I'm not really into water treatment. I just know the process. So if it's done, and even if it requires treatments, but I think the treatment is less effort consuming than the treatments of the chemicals.
You misunderstood the question. I asked of application of biodemogators on the oil spill.
Well.
Did you come up with something?
I haven't really thought about it, but I think the membranes are more effective for that. So I would.
Any other questions from the judges? Perfect. Yeah. Thank you very much.
Thank
Another
you.
round of applause for Jakob.
Thank you. Thank you.
And, oh, sorry, it's not on. A round of applause, please. Thank you very much. Contestants as well. Thank you very much. That brings us to a close of our master's presentations today. The judges will now take some time to deliberate. And we'll also be having a reflection soon. And then this afternoon we have our 2 PhD presentations. Hand over.
Well done, everyone. We'll take a 30-minute coffee break.